Hello, welcome to the demonstration of B-VNF blockchain-enabled VNF orchestration in MEC-5G networks. The demonstration covers what all technologies and software tools are used for the implementation of the DApp, how the registration of the three different entities happens in blockchain-enabled MEC-5G ecosystem, viewing and approval of VNF advertisement sent by third-party VNF provider, and so on and so forth. Let's have a look at the technologies and the software tools used for the development of the decentralized application, that is DApp. We use Metamask extension that can be downloaded on any browser, and it works as a bridge between browser and the Ethereum blockchain. We also use Web3.js to develop the client side of the DApp that interacts with the Ethereum. Next, we use ECIES.js, which is a JavaScript library that implements elliptic curve cryptography. This library is used to generate public-private key pair for each entity and is also used to generate session key. Next, we use AES-256, which is a NodeJS module and is used for symmetric encryption of the session key. Now, let's begin with registration of the three different entities in the system. To do so, an account needs to be selected from the Metamask extension. First, to register the VNF orchestrator, which is named as network admin, we select that account and enter the details as shown. This leads to calling of the corresponding function on the blockchain. The request gets processed as a transaction and it incurs some cost, that is Ether. On completion of the registration, the public-private key is generated. The public key is stored on the Ethereum blockchain and the private key gets downloaded locally. The private key of the VNF orchestrator is as shown. Same procedure is used to register two other entities, that is the MEC and the third-party VNF provider. Let's quickly register MEC entity and the third-party VNF provider entity. Now, let's look at the VNF advertisement and its approval. The third-party VNF provider advertises a VNF to the VNF orchestrator, which in turn takes a call whether to approve it or not. Before uploading, there is a need to create a session key which is used to ensure confidentiality. A unique session key is generated which is encrypted with the public keys of VNF orchestrator and MEC and are then uploaded on the Ethereum blockchain. The third-party VNF provider then uploads an exemplar VNF, which is Suricata in our demonstration, along with the system requirement details. The first upload button uploads the Suricata on the IPFS, whereas the second upload button pushes the metadata on the Ethereum, which incur the cost, that is Ether. Once the VNF is uploaded, the third-party VNF provider can send an advertisement to the VNF orchestrator. Let's go to the VNF orchestrator's dashboard to view the VNF advertisement. The VNF orchestrator can then approve it so that this VNF could be used in future on pay-as-you-go basis. Now, let's see how a service is requested by a user equipment, and to fulfill that service, how a VNF is migrated from the cloud, that is IPFS, to the MEC. For the purpose of demonstration, user equipment is mimicked by a web application which is different than the DApp. Let's first try to request the service number 2, which involves retrieving of a file which is not malicious. When this request reaches the MEC, it looks for the required VNF and the migration process starts. First, looking at the configuration details of the VNF to be migrated, The MEC checks whether it has enough free resources or not. In case it has, it retrieves IPFS hash of the VNF, which is encrypted with the session key. Using this session key, MEC decrypts the IPFS hash of the VNF and finally downloads the VNF from the cloud, that is IPFS. MEC then retrieves the encrypted session key from the Ethereum and decrypts it using its own private key. As mentioned before, Suricata has been used as an exemplar VNF. To instantiate Suricata, we use Docker container, which helps in creating a virtual machine. On successful migration of VNF, first feedback is sent. Let's now see what happens if user equipment tries to retrieve a malicious file. In this case, user equipment sends the request for service number 1. This time, the required VNF, that is Suricata, is already running at the MEC. Thus, it detects the malicious file and denies the retrieval of the file. When a migrated and instantiated VNF is not required anymore, then the MEC can decide to delete the VNF. At the time of deletion, the second feedback is sent by MEC, which gets stored on the blockchain and is used for updating the reputation of that VNF. It then makes the payment to the third-party VNF provider for the time duration for which VNF was used. Let's take a quick look on how the payment is made by the VNF orchestrator to the third-party VNF provider. VNF orchestrator can go to its dashboard to view the pending payment, if any. It then makes the payment to the third-party VNF provider for the time duration for which VNF was used. Of course, this process could be automated, but here we do it manually for the purpose of demonstration. Finally, let's take a glance on the two feedbacks sent by the MEC to the VNF orchestrator. The first feedback is sent at the time of successful instantiation of the VNF at the MEC node, whereas the second feedback shows the successful working of the VNF for the duration it was used. That's all, folks. Thank you for watching the demonstration.